colleagues of ours from TRE, Alice Robinson, who worked on the multiplier, Guy Edwards, who worked with me on things like the main machine and the B suits and so on, and Tommy Thomas, who worked on the magnetic drum, which I mentioned. There are some other people in the audience who make contributions to other machines in Manchester, but Tony said I must not stray and I must stick to Mark 1. So that I'm going to do. Now, Freddie Williams went to the States about the same time that Morris was referring to, 45 and 46, to contribute to a set of radar books which were being written. And he saw at Bell Labs some experiments on the cancellation of echoes, ground echoes in radar, which involved moving signals from a cathode ray tube obtained by putting a metal plate on the face of the cathode ray tube from one tube to another tube and then back again as a method of storage. Freddie came back to TRE, and about August, September time of 46, he started to set up this sort of system with a view to trying to store digital patterns. And by December, he had stored 1 digit at TRE. Able to draw this is it. We were interested in electrons, unlike Morris. In fact, we were interested in secondary electrons. And these give from a metal plate in front of a cathode ray tube this kind of signal if that pattern is drawn on a cathode ray tube. So that Freddie Williams' idea was that this pulse, which he called an anticipation pulse, told a circuit, or an individual, or you, that there was going to be this gap in the trace. And when the trace was switched on again, there was a positive pulse, which was the same area as this anticipation pulse. So this was called the anticipation pulse system. And, as I say, this was December 46. He invited me to, by that time I'd been in his group for 4 years, and he invited me to accompany him to Manchester. And I stayed as a member of TRE, but on outside duty in Manchester, in order that I could draw stores from TRE free of charge and suffice my project. For 3 months or so, largely at the beginning of 1947, I did experiments varying the speed of this trace and the focus of the trace and so on and so forth, and came to the conclusion that this pulse, which didn't play any part in the original anticipation pulse system, was much more useful than the anticipation pulse itself. And so, sometime in March of 47, I remember a session with Freddie Williams, and I convinced him that we should drop that pulse and use that pulse. And after some discussion, we agreed. Now, the reason the positive pulse is better is that it's more uniform over the whole face of the cathode ray tube. And also, as you'll see from some pictures I've got in the slide, the distinction here between a 1 and a 0 is between a negative pulse and 0, whereas the distinction on the positive pulse is between a positive pulse and a negative pulse, and any engineer knows that that gives you a better definition. So we switched to that scheme, and this resulted in a lot of schemes: dot dash system storage, and the focus system storage, which is the one that actually went into the current machine. So this original pulse that we started off with, in fact, was abandoned, and we switched to that system. If I could now show the first slide, how do I do? Do something with this. This shows the cathode ray tube. Something on the point.
Yes, it's on the desk.
Shows the cathode ray tube here, the face of the cathode ray tube. The metal plate, which, when this door is closed, clamps closely onto the face of the cathode tube and an amplifier. The whole thing is in a metal box because we found in early experiments that if you left the cathode ray tube in a wooden crate, which it came in, and just put a metal plate over it and then fasten that to the amplifier, that anybody riding down the road outside the lab on the motorbike would fill the whole thing with random noughts and ones. It's absolutely essential to have this screen. The signal here was of a few microamps, and this was an amplifier of gain about 1,000, giving an output signal of 10 or 20 volts. So that was the system. This is actually a rather elegant piece of engineering which was done by Ferrantis. Now the next one. This is the nice positive pulse here, and this is the anticipation pulse. And here we see a 1, a 0, and a 0. And these are just digit marks. So you can see that the distinction is between that rather fine positive pulse and that rather nice negative pulse. Now if you keep this in mind, you'll see that this is symmetrical with that. So the baseline here remains steady. Whatever pattern I write in, whether it's whatever noughts and ones pattern one puts in, the baseline remains steady. This is the spells out if you're in the right position cathode ray tube store, and it's 32 by 32, and you can see that this is the dot dash system. Dots for noughts, dashes for ones. And that sort of performance can be obtained, could be obtained at that time with an ordinary cathode ray tube. But of course, if you improve the cathode ray tube, you can get improved performance. And in particular, I remember a few things. If you use total glass for the cathode ray tube, then nasty charges built up on the surface of the glass which ruined the system. So lead glass was an advantage. The focus was also necessary. It was necessary to improve it in order to get any more digits on the tube. And so we asked GEC to develop a tube. It was also necessary that the screen on which these charges on the inside of the glass were deposited was pure. And IBM, who licensed this kind of store to start off their 700 series, told me that although they'd moved their cathode ray tube factory up the Hudson to Poughkeepsie to get rid of the dirt, they were actually troubled by pollen. So it's really quite an interesting thing. And of course, as you increased, as you made the focus much, much better, the necessity for a purer and purer screen became more important. So GEC did quite a lot of work on this cathode ray tube business, and this shows the most digits we ever stored on a cathode ray tube. It's the defocus focus system. Large dots are a defocus spot, representing a 1, a positive pulse, a negative pulse, and the small spots are a focus spot, representing a 0. On that screen there are 2,560 digits, and that is the state of affairs that is described in the little note I wrote, which some of you have got, which I submitted to Morris for inclusion in his conference. When we went to the Ferranti machine, in order to get the increased reliability that other speakers have spoken about, we halved the number of digits again and went back to 32 by 40 in order to make sure that the thing worked really well. If I'd been able to sit with it night and day, then I could have kept this working. But of course, you can't sit with it. So we made that concession of half the storage to reliability. Now, that is a picture of Freddie Williams. I've included that to include Freddie Williams, for those of you who've never met him. And you'll see that this machine is constructed of 19-inch racks. Because we've worked with them for 4 years at GRE in radar experiments. And this is a primitive form of VDU, which was a method of input to our computer with the cathode ray tube there and the keyboard here. Jeff Tootill said that this was actually Freddie Williams married me to the machine. Well, that actually was taken in June '48 when the first small machine worked. But it's interesting why we built that small machine. You see, here we had a cathode ray tube which would store patterns like that CRT store over long periods. But it wasn't really proof that the cathode ray tube system would work in computer, because if you at very high speed write noughts over ones, which is of course or ones over noughts, which is what you're doing in a computer constantly, the signals you get from the screen are not balanced in the way I described, because a nought over a one or a one over a nought is an unbalanced signal. So the baseline starts heaving up and down. We never seen this heaving up and down because we never fed it quickly enough. But we surmised that it would be there, and indeed it was. So I decided to design some test gear which would test this. But after a few weeks of, actually I was travelling into Yorkshire at the time, in that awful winter of 1947, and I did a lot of design on the train. And one of the conclusions I came to was that the only way to test whether the cathode ray tube system would work in a computer was in fact to build a computer. So I designed the smallest computer, which was a true computer, but it was a store program computer, which I could devise. And we ended up with one tube, 32 lines, an 8-digit machine. And this is a machine that you see there. The signals did in fact heave up and down, and the design of the amplifier and the clamping system to deal with it was quite an interesting exercise. Now, when that machine worked, I had, so to speak, completed my duty, because I'd been released to work on this system by TRE. And so I wrote up my thesis for a PhD on this system, and sort of less decided to almost take 3 months holiday before returning to TRE in December. This was June. But that didn't work out, and the reason was that we had a number of visitors. The most important of these were Sir Henry Tizard, who was the chairman of the Advisory Committee on Scientific Policy, and Sir Ben Lopspizer, who was the chief scientist, Minister of Supply. Now, they were very, very interested in the machine, and the upshot of this was that Ben Lopspizer arranged a contract which was given to Ferrantes to provide a copy of a machine which the university would design. So I spent the best part of the next 18 months designing that machine. However, the most interesting visitor, and the conversation I well remember, was Wilkie Wilkinson from NPL, who many of you will remember. Jim Wilkinson had in fact been a tutor of mine at Cambridge, so I'd met him before, but he came up one day and he was thrilled to see this machine working, because he'd been landed with a job of trying to make the NPL machine work. as we shall hear from Don Dave, no doubt. I remember during our conversation we discussed the length that a word should have, and we came up with the fact that 32 digits was a bit skimpy, and I wanted 40 digits because that enabled, as Morris described, to give me two 20-digit instructions per line. 20 digits were seemed quite generous at the time, but it was a fortunate decision because the invention of the B tube meant that we needed 3 of the instruction digits for the index rooms, or B tube. That was one thing we discussed. The other thing we discussed was single and double length instructions. And we came to an agreement that a double length instruction, that is one with 2 addresses, double instruction, was worth 1.3 times a single address instruction. And this confirmed me in the view that we should indeed stick to a single address instruction. Going to a double length instruction was not worth it on any grounds and would have ruled out having 2 instructions per word in any case. So that was a most interesting conversation that I had with Wilkinson. Now, we then went on from about October, when the contract with Ferrantis was signed, November I think it was signed. We went on to design substantially larger machines, in which there were 2 main features which stand out above all the others. One was the invention of the B line, which is quite an interesting story. Most of the people working there were thinking of different structures. The people I'm considering are Williams, myself, Newman, and Tutiel. We were considering possible different structures, things like 2 accumulators, and so on and so forth. I'll give you my example. I was interested in splitting the instructions from the numbers, because this would have allowed me to double the speed of the machine, because whilst extracting a number from one half of the store, I could have been getting the next instruction from the other half of the store. But I was advised by all the programmers I spoke to that I couldn't do this. So the next thing I proposed was that we should have a separate accumulator for instructions. Would that be all right? And the answer was still no. But you see the kind of thing that was going on. We were trying to think of different structures. Now, in one conversation, the 4 people I've mentioned, there was a discussion, and out of this came the index register as being the best new suggestion for the machine. And so we put in the B tube. It's called the B tube because we had an accumulator and a control, A and C, and so we called it B. The other very interesting feature is that we decided to link the cathode ray tube store to a backing store using a magnetic drum. And the magnetic drum, in the paper that some of you have, which is the one at the time of Morris's conference, was 1,024 words, and it was a 10-digit system. In fact, all our work was done at 10 digits, 10 microseconds, sorry, 10 microseconds, and that made it very much easier than the microsecond that Morris was trying to deal with. The cathode ray tube store ran at 8.5 microseconds in its early days, but when it went into practically again for practical reasons, we expanded it to 10 microseconds. So we of course, the immediate access feature of the cathode ray tube store more than compensated for this slower digit. That is to say, we could switch to any line within 40 microseconds. And this couldn't be done, of course, with any delay line system. So we came out with much the same speeds of things as the Morris been talking about. Speeds of instructions. There's an interesting thing about the magnetic drum and the order code. In the order code, I introduced a relative control transfer with the idea that if, say, a subroutine were put in a different place in the store from which it had been programmed, the relative control transfer would not need to be changed, because it simply moves back and forward relative to the instruction at which you were at. The other thing was, I put a tagline, which we call the 65th line, on each of the pages or blocks of words on the magnetic drum. So that there were 64 useful lines and a tagline, 65th line. This was with some vague notion that programmers would be able to move tracks around on the drum, not necessarily in the fixed order in which they had originally appeared on the drum, and still keep track of them. Now, the programmers who used the machine never took advantage of this, but these two sorts of ideas were the seed of the virtual memory and the one-level store which came along with the later machine. So those are of special interest to me. There was a lot of discussion about, I think everybody had a lot of discussion about the incidence of the various orders, that is, in particular, how many multiplications would there be relative to all the other instructions. And in the early days of the Ferranti Mark I, this is giving the answer, whereas the decisions were taken before we knew the answer. But it's better to give you the answer than speculate endlessly. 16% of all time was spent on magnetic drum transfers. Magnetic drum transfers. 28% was spent on multiplication. And 56% of the time was spent on the other orders, like addition, reorders, and so on. Now, what that means is that if we had gone into the Ferranti machine design with a slow multiplier, the machine would have, in fact, have been 5 times slower than was the actual case, because what we did was choose that degree of parallel multiplier which made sense. These orders took 1.2 milliseconds and 9 milliseconds if there were B orders, and the multiplier took 2.16 milliseconds. Now that parallel multiplier was a half parallel multiplier. It multiplied 40 digits by 20 and then 40 digits by the remaining 20. So that 2 stabs were taken to get a 40 times 40 multiplication, and that took a total time of 2.16 milliseconds. So that the quite surprising thing also of these figures mean that if you just fiddle around with those numbers, you'll see that 1 in 5 of all orders obeyed, not written, we're talking about orders obeyed, 1 in 5 of all orders obeyed were multiplications, which is really quite startling. How long have I got? 5 minutes. There was a great interest, with Newman being in Manchester, in number theory at that time, and so I put in some special orders along these lines to which might interest especially those who have got the paper. If you imagine that these lines represent 40-digit numbers, we're interested in multi-length numbers or number theory. That is to say, in that particular example, the whole of this is 120-digit number. Then if we take a simple example and we want to add two of these, we will get a carry in this position from, or we make the carry in this position from the sum of these two. Now, this area is the most is the accumulator, and the area here in which this carry has appeared is the most significant part of the accumulator. So that we've added two numbers, two 40 digits, because that's all we can add in the accumulator, and produce the carry in the most significant digit. Now, I produced an order which then switched the significance of the accumulator so that this position became the least part of the accumulator, and that position became the most. So that became a digit in the least position for this next addition, and so on. And this order I call reverse A, because it costs one flip-flop, which is rather cheap. Now, if any of you are sufficiently interested, you can try multiplying together 3-digit numbers, and you will find why 320-digit numbers. Suppose you multiply those two numbers together instead of adding them. It becomes quite complex. And if you use the orders I've provided in that list that some of you have got, you'll see why I provided them. Now, of course, in the whole context of computing, that was a complete dead end, if you like, because if anyone was interested in that in a modern computer, they could take enormous trouble to do it, because they would be about the only person interested in that sort of work. So it wasn't a development which lasted, and in fact, within a couple of years of completing the design of the Franklin machine, which was done by October 1949, so that by 51, when the Franklin machine was delivered, I and Diables and Tommy Thomas were already thinking of building a second machine, which went to the other extreme and used hardware floating point arithmetic. So there you are, Tony, who said I mustn't speak about anything but Mark 1. So I'll finish. Thank you.
Would you care to answer the questions? Do we have any questions, please?
I was reading through the BCS booklet, which was published when Professor Ershoff came over a few years ago and he gave a lecture to it. And in there was a table describing some of the early Russian machines. And I noticed in there that around 1952, they were talking about using CRT stores in their machines. And I wonder if that was a separate development, or whether they somehow learned what was going on here and reproduced it. Did you ever come across that?
Well, as I understand it, the position is this, that there's an academician called Lebedev who worked in Moscow, who was interested in computers. But Stalin, in 1948, stopped all work on computers for some reason which I never understood. And Lebedev persevered with this, and he showed me this machine that you're speaking of, using cathode ray tube storage in Moscow in 1960. And that's all I know about it. It was in a lovely appropriately by then, of course, because the cathode ray tube system was oxygen. It was in a kind of a boarding room with red velvet curtains draped down.
But your work has been published long before that.
That's right, yes. I don't think it was I'm sure it wasn't. They didn't claim it was independent.
No.
But they didn't get away to the quick start they wanted because of this decree saying they couldn't work on it.
Tell us about sideways edition.
Sideways edition.
Oh, no.
The number of ones.
That's right.
In
You were
the
famous
line.
for saying what we call sideways edition.
Well, I wasn't famous for it. I just had the unfortunate job of implementing it. There were two things in the Mark I which Kilurn suggested. One was that, and the other was much more useful because it became the basis of earning. It was a random number generator. And there were two orders which Kilurn was responsible for. Those were the ones.
You said you went to the States, and this was one of the triggering points. And also Morrison went to the States, and that was one of the triggering points for him. Were the triggering points essentially meeting? You didn't actually say who you went to, at least Morrison. Did you go to see the ENAC people? Were they a trigger point, or who was it actually that fired things off?
I did mention that the Calibrative store came out of analog experiments on radar. So far as I was concerned, you see, this Calibrative store was the first immediate access store to work. So a lot of the design, which centered around the Mercury delay line, and we shall hear more of that from Donald Davis, was because the store wasn't an immediate access store. So the things I needed to know in order to build those machines were very small, and they were known to Babbage, I believe. The machine had three parts: store, control, and accumulator. There were things called instructions which had an address and function. There was a control transfer, and there was a test instruction. Now, on that, so I may have missed one point, but I can't honestly tell you where that small number of sacks actually came from. What I know was that there was certainly current, both in this country and in the States, by December 1946, when we moved up to Manchester.
No, I thought they'd been very well known.
Since 1850.
Yes,
You're probably right.
It's actually just, perhaps, could I ask?
Could we just say that there is going to be a general discussion after the next presentation, and I think this is a sort of question which might go better there, if you don't mind. Any other points specifically on the Manchester machines?
I got the logic diagram that Mark on here.
Give your name, please.
Dick Grimstone. The Franti Mark I logic diagram. These are flip-flops. It shows a fair level of detail. The magnetic drum is here, and the cathode ray is here.
There's nothing to it, I think. I mean, not a repetition of the same thing, which is not drawn.
No, I think that must be more like
It's more or less everything.
perhaps some of the things represent 20 flip-flops.
Perhaps we would be able to have a copy of that and
Yes.
Thank you very much indeed.
I'd just like to mention one boundary condition which we had, which might interest you, which was when we got associated, we'd been associated with Ferrantes on radar, but when we got associated on the computer business, I asked them what the price of a flip-flop would be. And that's a 2-valve flip-flop in order to get just a view. And the answer was £20. So that one bit in fermionic valve cost £20 in 1949 rate. So if you multiply that by 15, something like £300 for one flip-flop bit. So that was the sort of one of the factors against which we were working, all of us. Even Morris, who was lucky enough not to worry.
Okay, thank you very much indeed. Well, now I'd like for us to hear about Harvard Ace, and perhaps Donald Davis could tell us about that.
The origins of the ACE, by the way, automatic computing engine, engine by reference to the to Babbage, of course, and the origins were a report by Turing in 1945 to the executive committee of the laboratory, which actually had to approve the project, which they did. And this report actually is a remarkable document, has been reprinted recently, it is available, and sets out the reasons for doing the project and what Turing believes the machine should be. The kind of calculations that he describes are partly numerical calculations of interest to scientists and engineers. He also describes the use of it for clerical work and says that he won't attempt to do this because of the large amount of input and output, and he wants to avoid this problem. He talks also about logical problems, combinatorial problems, number theory, and what else? I don't think it's in that report, but I remember discussing with him the use of these machines for weather forecasting. So it had a very wide range of intended uses, mostly in the nature of large-scale mathematical calculations. In fact, the people who came into the project all had a background in large-scale numerical work. Turing himself, of course, in cryptanalysis, well, he must indeed have felt the need for large amount of computing, which they didn't have, except the Colossus, which was a very special purpose machine that he helped with. There was Jim Wilkinson, who came from working in ballistics calculations. So I think Tom Vickers was with him at Fort Hostel. Tom Vickers was here today. I came in much later, but my background was in the Tuvalu's project for building an atomic bomb, where we had to do enormous amounts of calculation just with large numbers of people turning Bunsen levers. So we were all of us well aware of this kind of requirement. That's what drove the project. Turing's report doesn't justify very much the individual details of the design, so one has to guess a little bit there. But the main interesting feature of the ACE that he was describing there was optimum programming. That's been hinted at already. He was already convinced that it had to be a delay line store. He hadn't heard of any other possibilities, and so that's what he chose. And the delay line store, you have to wait for the numbers to come round. And he wanted some way of avoiding some of the cost and time that this caused. And the technique was to place the instructions around in the delay lines so they came up at the right times when you needed them, to use a judicious mixture of short delay lines, single, double, quadruple word, 4-word, and long ones of 32 words, and be very clever in the way you laid out your information, your data, so that you could, generally speaking, avoid the latency problem. Also, when you wanted to take numbers sequentially out of a delay line, arrange for the thing to precess, so that every time you took a number out, you shortened it for a short while and let it go around and come back with all the numbers shifted around one place. All these were clever tricks, and they did, in fact, in the end, have a very considerable effect on the speed of operation. But of course, they made programming into an entirely different kind of problem. You first had to solve the programming problem, then you had to solve a nice little puzzle, which is where to put all the things into the delay lines, and so programming had a second step. Clearly this wasn't a machine designed for everyday people coming in and using it the way that we use personal computers and so on, for high-level languages and so on. It was a machine designed for people who were devoted to programming and getting the maximum speed out of the machine. That was the way Turing conceived it, and it was never questioned after that. So it wasn't a question of carefully thinking out the strategy, a question that he made that choice, and it was natural, I think, for Turing, who was a man who liked to solve complex problems. He tended to do things in a complex way, if that was possible, and I think it was part of it. all the stories that you read in his biography, his telling. Remember how he worked out that there was a link missing in the chain of his bicycle. He worked out that he could turn his the crank round by so many revolutions, then he could get off and then he placed the chain on the bicycle. It was much better than actually mending the link. Well, that business of solving problems, I think, may have driven this decision. It turned out to be an interesting and useful decision if you had to work with this kind of store. Of course, as soon as we had easily available random access stores, it was no longer of any interest. So it was a temporary phase in the history of computing, an interesting one, and one that did extract useful speed. Now, it was particularly valuable when you had the opportunity to spend a lot of time optimizing a very small part of the program. And that often happens. The inner loop is worth spending some trouble on. And so the machine, when it was finally working, tended to specialize in its applications. And numerical analysis, of course, in general, but in particular, the manipulation of linear equations, of matrices, and it ended up with a vast library of extremely powerful functions to perform on matrices, which turned in the end into an interpretive system which you could quickly assemble these various bricks, as they were called, to do matrix operations with enormous efficiency. So that in fact, when it was all working, its major applications for a long time were in the aircraft industry, working out flutter problems, which had become very necessary. That was just the time when flutter became a problem and when it was necessary for the certification of an aircraft that it had flutter calculations worked up. And so the Canberra bomber and a large number of other planes had their flutter calculations done on this machine. So that's the sort of background to the peculiar way in which the machine was designed. I want to give you an idea of the historical sequence, which does affect the decisions. Turing's proposal... I'm sorry. Turing's proposal was in 45. We carried out, a lot of design studies were carried out. A group in the mathematics division kept writing programs to see if they could get the design better and better. And meanwhile, hardware was being developed by a post-office research station at Dollis Hill. This has an interesting background too. During the discussion at the executive committee, it seems that one of the people there was actually wanting the computer to be designed and developed because of the requirements of cryptanalysis. Therefore, Turing's background at Bletchley Park had something to do with it. And in fact, the very people who worked on Colossus at Dollis Hill were brought into this team and ran the team at Dollis Hill to do this. But this arrangement didn't work well. And in fact, there were at least two very bad hiccups in the organisation. This was one of them. It didn't work well, and in the end we separated. And interestingly enough, Dollis Hill went ahead to build the ACE computer. We actually provided the design for much of it, and it became the Mosaic, which was an Ministry of Defence machine, which you may have heard of. That was the ACE under another name. The same development continuing its momentum at Dollis Hill. Then Harry Husky came from America. He worked on ENIAC and put a lot of energy into the team, which was flagging a little bit from the sort of rather poor beginning that started. And he hatched up the idea of building a test assembly in order to be able to try out the principles of the machine quickly. And in fact, that was a very simple design, and here is its complete logic diagram, in which I can guarantee every trigger and every gate is written out separately in this diagram. So it's all there. And in fact, this was the genesis of the pilot model. The test assembly was never completed. We began building it. Its electronic design was a bit hairy. I personally wonder whether it would ever work. Some of its mechanical design was a bit hairy. And a few months after Husky left, it was decided to close down the development of the test assembly. I had a part in that decision. But I think it was probably the right decision. But still things didn't go very well. In 48, two separate teams were working at NPL, one in what was called the electronics section, and the other one, the maths people continuing with their programming, which was getting very boring to program machines that we write programs you can never test. The one thing we knew they would be full of bugs, and we couldn't find them. So it was getting a bit tedious, and I'm not quite sure of the exact dates, but roughly speaking, fairly early in 49, this all came finally together. And as you can see, a tremendous amount, 3 years have been wasted really in this procedure. But at that stage, all the people in the maths division interested got up and marched across to the electronics section and sat down there, and everybody started building, and we'd forgotten about programming and actually started solving lines. And from then on, it all worked extremely well. I must also say that a number of new personalities have come in this time. In particular, Ted Newman and David Clayden here from EMI had brought in a tremendous amount of experience in electronics design, coming from radar work and pre-war television work, and David will tell us something about that. So we had a lot of input there, and Fred Osborne came in to help us with mechanical design. He is here. Also Mr. Colebrook took over the leadership of the team, and for the first time brought in a strong leadership of a combined team. And from that time on, things worked very fast, so that the first programs were running rather haltingly in 1950, and by about the end of 1950 we were running useful programs. I remember I was running ray tracing programs. In 51 we had a multiplier fitted and a new control system which saved on some of the logic which Ted Newman designed was put in, and that virtually was then the completion of its development, apart from the magnetic drum which came about 54 and which was very important for its application. It was operating as a service from 1952 onwards, was moved to a new location, and it really was, it may have been one of the first really working commercial services. We were selling our services to industry, partly the aircraft industry. I worked for the Safety and Mines Research Board, I remember. I did some work for what is his name now, the people who deal with motor traffic. I did some work on traffic lights. Everybody was very busy with using it as a real service. So that's a little bit of the history. As you can see, it came from Husky's original idea, which in fact Turing supported. Turing had left us in the meantime to go first to Cambridge and then on to Manchester University. Now, the peculiarity of optimum programming is that you have to have a fairly complicated instruction to deal with. This shows the form of the instruction, where the first field here is a 3-digit field giving you the next instruction source. That's the tank from which you'll take the next instruction. Then the source and destination. Now the sources and destinations are not just stores. The sources and destinations actually carry with them the operation code. So everything about the operation is defined by means of the source and the destination, which is another peculiar property introduced, I think, principally for the pilot model. Then there are 2 timing numbers, a wait and a timing number, and a go digit, which helps to allow you to stop when you want to and be able to step on. It's quite important for synchronizing input and output. The transfers that you could carry out were either single transfers or multiple ones. Multiple ones could be very valuable. They could, for example, transfer the whole of a tank into another tank in one instruction, or they could add a whole series of numbers into one short tank, or into one double-length tank, or quadruple-length tank in one instruction. So there was a little bit of vector operation here. Rather primitive, but it was the sort of thing that now appears in large number of countries, was here in a primitive form. Now, the wait, in fact, was the time before the transfer started. The timing number determined the end of the transfer, and then immediately afterwards you got the next instruction. Or you could have this single serial bit here set, in which case you got a single operation which you could ship anywhere in the field, and leaving the next instruction fixed. So it was quite complicated, but of course quite powerful if you knew how to use it. Very tricky to do well. And just to show you the kind of functional sources and destinations that we have here, you see that it's a fairly complicated table of sources and destinations. Just to give you an example, if I send things to TS, that's a temporary store, a short store, 26 and 27, I can get out logical operations and an XOR out of them. By sending them here, I multiply them, I can add and subtract into an accumulator and so on. or send them to the punch. A very clever thing here, I think rather like the clever scheme used in Cambridge, is the way you deal with initial orders. You've got somehow to get the whole thing started. And what was done here was to arrange that the first instruction was always zeros. It starts off with the instruction register cleared as soon as you push the initial input key, and that means you take the input off the Hollerith machine and send it to straight into the instruction register, which means that you obey the first line of that's on the card. The card, by the way, is punched horizontally, not the way a Hollerith card is meant to be punched, but it can be punched in binary, 32 bits across the card. It makes the card into rather like lace when it's being well punched. It turns out that the cards can actually still feed through like that. We did other clever things like pushing the chads back in when we want to. Perfectly standard technique. After a while, it was a good idea to reproduce the card. So I won't go into detail, it will take too long, but you can see that by choosing your source and destination, you actually decided what the operation was. You have a separate opcode. Just a word about input and output. Again, almost without thinking deeply about it, we chose Hollerith machines. There were Hollerith machines all over the place in the mathematics division anyway, and we knew them well. It fell to me after Stanley Gill left to actually do the engineering of the Hollerith machine input and output. I had all the problems of noise and so on. But we solved them very well, and we introduced later faster machines. This gave us a very high speed of input. We were taking in 12 32-bit numbers per card at 100 cards, coming in at 200 cards per minute, eventually going out at 100 cards per minute, which was a very great deal faster than we could have done with paper tape. And it was eventually, in fact fairly soon, highly reliable. Meant a lot of careful adjustments, and one had to know how to adjust Hollerith machines, but we learned how to do that. Now this actually turned out to be our first level of store. Long before we had the magnetic drum, it was quite common in large matrix operations to be continually punching out onto cards, and then even sometimes rearranging the cards as part of the algorithm and putting them back into the input reader again. This was therefore a very tedious process, but treating the machine really rather like a complex Hollerith machine. But it was very powerful, and it was all we had. That way we could invert very large matrices that couldn't have been done any other way. And the operators became extremely skilled in handling of cards. So that was the background to the sort of system design of this machine. Now, just to sort of summarise, the thing came as a requirement of the mathematics division, with numerical analysis as the driving force. It was aimed at the fastest operation that we could get, given that the delay line was going to be the memory. Went through a number of stages. Eventually ACE was built, but by that time was a dinosaur. It was out of its time. Already 4 stores had been invented, and I tried to deflect the ACE in that direction at one time and didn't succeed. It had too much momentum. So there was a 3-year delay as a result of, I suppose, organisational problems. The pilot model achieved all its objectives. It was fast, it was very simple, and 800 valves, which is pretty much a record. It led to 3 machines, of course. I mentioned Berzé, to Deuce, of which I think 32 were made, and very widely used, to the Bendix G15, which was made in USA after Husky went back. He designed this around a magnetic drum, replacing the tanks by a magnetic drum. In fact, the drum had 2 heads. You actually read and wrote and rewrote onto the drum. It was not a normal kind of drum. It was rewritten every time it went round. So it was a very strange drum. And the Bendix was a successful machine. 400 were made. The 400th was the last one. It was gold-plated. And the Husky had one in his garage. So he must have been the first person to have a personal computer. It gave out enormous quantities of heat in the Berkeley sun. It was rather unpleasant, but it worked. So it had a lot of projects, and the ACE was eventually built. At that point, I'd like to hand over to David Clayden to talk about some of the engineering aspects of the ACE. Thank you.
there were we finding ourselves in radio edition of NPL, whereas Donald and most of the other people he has mentioned were at the far end of the laboratory in math division. Now, my first job was, in fact, to make one of those items of equipment you mentioned there work. That was a mercury delay line, work with some electronics which had been made by a contractor. Now, it occurs to me that we've had much talk of mercury delay lines, but nobody has actually mentioned in detail how they are made. And I have here a diagram which I have rapidly made, which shows some of the detail. Essentially, you have a column of mercury which goes on and on that way. Here is the crystal, piezoelectric crystal, which is driven by this electrode. You notice a gap between the electrode and the crystal. This is very important because if the electrode touches the crystal, it dampens it enormously. So it's capacitively coupled to the crystal. The mercury makes contact with this side of the crystal. The whole thing is sealed, you hope, sealed, so that the mercury doesn't run round behind the crystal and get in contact with the electrode and so on. This is a lump of insulator. The whole thing is held together with bolts. So you apply quite a large voltage, oscillating voltage. We in fact use 15 megahertz on ours. Drive the electrode, which drives a sonic pulse through the mercury via a piezoelectric crystal. You have the same thing at the other end, and the crystal at the other end gives you a voltage for the inputs of the sonic wave. The total attenuation in the long mercury delay line, by the way, was about 60 dB. That is 1,000 to 1. So you need a receiver at the far end, and indeed you need a receiver with a good deal of constancy in its gain. Anyway, that's a little aside, perhaps, on the subject of mercury delay lines. Now, Ted Newman and I arrived, having worked during the war and subsequently at EMI at Hayes, where we had learned much about technology from H.D. Bloomline, who had invented the cathode follower, the long-tailed pair, I think before the war. I'm not quite sure when he did that. But anyway, the contrast that struck me when I got to NPL was that at EMI, nearly all cathodes were not connected to Earth, whereas in the rest of the world, nearly all cathodes were connected to Earth. And the contrast was quite enormous. I have here a circuit diagram of a typical circuit. A typical circuit that we developed for the ACE pilot model. Here we have a long-tailed pair, double triode. The current is defined because this end of this resistor goes to minus 300 volts. Those two grids sit at about 200 volts. So we have like 100 volts across 33K, which gives us a defined 3 milliamps. And it doesn't matter what the grid bias is on these valves. So that as the valves deteriorate, we don't run into bother until the grid's actually running with coupling. So it's a fairly reliable technology from that point of view. Now, in this particular case here, we have a double triode. If this grid is higher than this grid, then all the current goes up that way. And if that grid is lower than that grid, all the current goes up that way. Here we have two more splits. When the current gets there, it either goes that way or that way, depending on where that grid is. That grid also connects there. The current going up this way either goes that way or that way. The two inputs. There's one input there, the other input here, which is coupled down on that valve there. So if both of these grids are up, all the current goes that way, and we've got AND output. If one grid is down, the other grid is up, and the current either goes that way to there, or goes up that way to there, those two things together, so that's XOR output, that is different. Else all current goes up this way, we don't want to know about it. This is another piece of standard technology known as a DC coupling, where we have the signal up in the region of plus 200 volts, and we want to get it down to the level of minus 200 volts. We have a network consisting of 4 resistors and 2 capacitors, and the time constant goes to match exactly, and the current works beautifully. Those are just two examples of technology. Another piece of technology is here. If we feed clock pulses in here, our clock pulses are typically 1/3 of a microsecond in every 1 microsecond. So the current went up here for 1/3 of the time. It was capacitively coupled into these cathodes, so that with an average current up here 3 milliamps, the current up here was either 10 milliamps for 1/3 of the time, or 0 the rest of the time. So we've defined 10 milliamps current up there. That is a typical example of the sort of technology that went into our circuits. Now, coming back to mercury delay lines, I showed you one end of, a cross-section of one end of the mercury delay line. We started off with long and short horizontal delay lines. Subsequently, we developed the vertical delay lines. This is a delay line for one word, that is 32 microseconds. It's a late development of the scene. Subsequently, we built other sizes. This one is 4 words, that is 128 microseconds. And the initial long delay lines were all long horizontal ones, rather like John Pinkerton showed us in this picture. Subsequently, Donald Davis invented the folded long delay line. This one which was this way up. There are 2 reflectors at the bottom and 2 crystals at the top here. So the signal went down one tube and across up the other tube to receive the far end. And that was a latish development, but the delay lines in the juice were all of this design, I think. Is there anybody wishing to know more about mercury delay lines and storage technology? Perhaps I can refer them to that paper, which was published in the IEEE 53. Now, I next want to talk about the magnetic drum. We needed a backing store for the base pilot model to provide us with more storage capacity, and we wondered for a long time how we would best do it. We said to ourselves, wouldn't it be nice if every track on the drum stored exactly the number of bits in one long mercury delay line, so that we could do a total transfer from one to the other in one revolution of the drum, transfer all the bits from one to the other. We wish to avoid having a lot of buffer storage in the way, and concluded the only way to do this was to synchronize the drum to the machine. We did some arithmetic about this and concluded that if we ran the drum at 1/9 of the speed of the mercury delay line, we would indeed be able to transfer the whole of the content one way or the other in exactly one revolution of the drum, being 9 revolutions of the mercury delay line. And we worked out a system where we could do this on condition that we exactly synchronized drum to the mercury delay line within an accuracy of plus or minus 4 microseconds. We consulted the experts about this, and they said, oh no, that's quite impossible. So we went away and did it. And this is the details of the drum we finished up with. As it says here, drum revolution 9 milliseconds. The bit time was 9 microseconds, that's 11,050 seconds. And 1024 bits transferred was 9 milliseconds. We had 16 reading and 16 recording heads to access tracks. They were shiftable to 8 positions, so we had altogether 128 tracks, 124 bits, which gave us that as the total capacity. The way we managed to get this synchronization to work was due to hysteresis motor, which runs, when it's running, behaves like a synchronous motor, and we were then able to control the phase of its drive to get it to synchronize accurately to the main clock register. Now, we subsequently went on, that is the pilot model drum, we subsequently went on to develop the ACE drum. And rather than show you a slide of it, I have here the actual thing. The drum is inside there. This is the drive motor on the top. And behind here is the actuator for the heads, which is a moving coil magnet. And that drives the heads, which are down there, up and down 16 positions. And the performance of that was really rather remarkable, I think, even by today's standards. The drum revolution time was 5 milliseconds, which is 200 revs a second. The peripheral velocity is in fact knocking on 200 miles an hour. The bit rate is a third of a megacycle. So that was approaching the mercury delay line rate of EDSAT, which was half the megacycle. Anyway, enough said that. Now, we subsequently, as Donald remarked, went on to design the big ACE stuff. And I'd like to make a few remarks about that. It was in fact a 3-address machine. The pilot model was produced with 2-address machines. The big ACE was a 3-address machine. It had 2 source highways, 1 destination highway. They all went via a function unit, so that you could take 2 words out of mercury delay lines and, for instance, add them together and put the result back in mercury all in 1 word time. Moreover, we eliminated the time wasting time between instructions, as I mentioned, so we could, in fact, in the best instances, do successive operations and taking 32 microseconds each. Now, we increased the word time of the word length of this machine to 48 bits. We've had some discussion of the number of bits in the word. Here we had 48, and that gave us enough bits in the word to control both sources and the destination and the timing of the instruction. Here we see mentioned the magnetic drum store. We in fact had 4 of these drums on the ace, and that gave us 32,000 words of information. It also had an autonomous multiplier and an autonomous divider. So although multiplication, for instance, took about half a millisecond, you could set it going and come back and collect the stuff later on while we were doing something else in the function. But I think that's all I have to say. Please welcome questions.
You mentioned that there was a space behind the crystal. What was there to stop the crystal getting bent by the pressure of the mercury? They're going to keep the crystal dead flat.
Okay. The hydraulic pressure on the crystal was in fact kept very small, no more than or less than an inch of hydraulic pressure. So the bending of the crystal was very strict.
I'm surprised to find it necessary to do that because the ley lines which I was familiar with, we had the crystal backed up with an electrode. It was really touching it, but it didn't make acoustic contact, so there wasn't really any fantastic effect as far as we knew.
There's no question of resonance. The crystal was dragging like crystal.
Yes, yes, heavily
It
damped.
wasn't heavily damped. It was not damped. It wouldn't be transferring.
Well,
I can make a comment on that really, because one of the troubles is the question of wetting, or at least effectively being in direct contact with the mercury and the crystal. And to do that really is make it safe, so you don't, without a lot of pressure, you need to have it wet. But it so happens that if you use extremely pure mercury down to wet the crystal. And that's what we use. I found it out because a friend of mine who works in the Scientific Instruments Research Association in Chislehurst, he knew all about whether you could wet crystals with mercury or not. And that's how we could do it. We could do it because we used extremely pure mercury. We knew how pure it had to be. And then it wet the, it actually wet the crystal, there's no problem.
Yes, but you have to polish the crystal.
We have to polish the crystal as well, they're very high degree.
Yes, but do you remember why we had a gap between the electrode and the crystal?
I can't remember that. No, I can't. I've forgotten. But certainly the essential thing was that why it worked with very low pressures and that was it went.
All right.
Yes, now we work on exactly opposite principles. I know that if you have polished crystal and clean mercury, the mercury wets the crystal. But as we done the other way, they were not polished crystal, they were brown, therefore cheaper. And the method of getting a good contact was to fill the tanks first with alcohol, then pour in the mercury. To displace the alcohol, to begin with there would be a thin film of alcohol between the crystal and the mercury. That would disappear after a time, and the mercury came in contact.
Our solution was similar, but slightly different. we thought that the alcohol tended to disappear, it to evaporate. So we decided to use a very slightly diluted solution of glycerin, 10% water in glycerin, with a certain amount of anti-rusting agent, stop rusting inside the tube. And that did work very well. The tubes remained in good condition for about 15 years after that.
Well, anyway, I expect the audience will appreciate there's a deal of black magic.
When you said the signal was reflected at the end of the temperature, is that the sonic signal being
Yes.
reflected?
Yes. Yes, there's a double reflection.
Just mercury all the way through.
Just mercury.
How did you deal with the problems of reflection in short length?
Piece of gauze across. Well, in the early ones, we had a piece of gauze across. But what I do not remember is what we did in these. And now, Fred Osborne is there.
Same thing on the
It's the same. We use gauze, do we? 45 degrees gauze.
We could have untouched some steel or something which was good absorbent and it was matched to the crystal back instead of that. I'm not sure whether we did it. This is enough for us to get a black magic, I think.
There is a small point that people might be interested in about these delay lines that went first one way and the other, because it's a bit difficult to get them right. And of course our director at that time was a Darwin and therefore belonged to the Wedgwood people. And because of this, what we did was to put a wedge of wood into the but that made it all right.
It occurs to me that there are 3 slides up there which I've forgotten about. I wonder if
Yes.
it's possibly just Now this is a photograph of the ACE pilot model, which incidentally is to be seen for real in the Science Museum. And here are the short mercury delay lines. These here are 2 early reflecting ones, like the one I've just shown. And in the box at the back are some other mercury delays, so I've got it down there, are the old horizontal ones. That, strangely enough, is George Davis, who's in there. And that is an early control desk. And here we have the card punch and the card reader. This is a photograph of the magnetic drum for the pilot model. Here is the drum surface. If you look carefully, you can see some scratches on it where the legs have actually touched down. But since the surface velocity on the pilot model was about 90 miles an hour, we had to be rather careful that the heads didn't touch the drum. Here's a stack of heads. And this is an actuator. Now, this photograph is actually of a 2-position actuator which pushes the heads up and down 1 of 2 positions. Those actuators were subsequently replaced by 8-position ones. And we in fact have designed and made a 16-position actuator which did not prove to be reliable, so the machine finished up with an 8-position actuator. Now just here, very difficult to see, is actually a toothed ring on top of the drum which had 1,024 teeth on it, and that was used to generate the top pulses for the whole thing. This is a photograph of the big case in which we expanded. We felt we needed elbow room. It was made with quite big panels there. That, strangely enough, is Patwood Rock, who's sitting over there. I can't remember who that is. That was a young lady we used to have. And each one of these cabinets had a large door which slid up and down. The whole of these cabinets were cooled by an air circulating system through a duct under the floor, and the water cooling went out to an outside cooling unit. This is the control system. Thank you very much. I think we've finished with the slides.
Thank you very much indeed. discussion, and perhaps we could pick up the point raised earlier about the origins of some of the ideas that came into the design decisions of these early producers. And perhaps I think where the point at which I interrupted the discussion was that we mentioned the influence of the American scene. Obviously, the influence was very direct on Royce Wilkes's ideas, and Tom Kilurn has already indicated that because of the way he approached the design, it was less of an influence. Did the Pioneer people have any influence? Do you see any influence from the American work on computers, or did they feel that they came from it?
In fact, we had the report on the exact available while we were doing the early design, and so we knew about the single address machines and so on. But I think that, in fact, the ideas were so much driven by Turing's concept of what the age should be, that these ideas were not well received. So, to that extent, although Turing had spent some time, you would say, there wasn't a very direct connection. I'm not saying that's a virtue, but that's how it was.
What was your perception, Maurice?
There was work that went on in Philadelphia that led to the design of the ENIAC, which was a dinosaur machine that had 18,000 vacuums. While that was being done, Eckert and Morton began to realize by the application of logical principles we could do better. Eckert invented the mercury tank, the memory, and certainly Turing knew about that because there's a reference to it in a paper of his that was published much later, but written earlier. This group was joined by von Neumann, and out of that little group came these ideas of the stored program, the idea of instructions, the idea of all these ideas we have. That, of course, led to a number of different kinds of machines with different numbers of addresses, parallel, serial, and so on. But they were all really, as I see, based on those ideas that came out of that group in Philadelphia. Who contributed what, no one will ever know. There was, some years ago, a tendency to give von Neumann all the credit, but von Neumann, that was went on. Eckert, I think, had the major part of the credit, von Neumann has some, but it was from that little group, these basic ideas which then spread and led to various things.
I think the idea of the stored programming computer probably goes back further than that, though. I mean, it was inherent in Turing's 1936 paper, which in fact not only had was a stored programming computer in the sense that the instructions were stored and interpreted in the store. I mean, it was a very funny machine. But to also, in fact, contain the idea of interpreting a program language. So a lot of very basic mathematical. Now, how much influence they had on later development, I think is very questionable. But the concept was there.
Well, all I can say is that anybody who thinks in the computer field now, who thinks that that they came from that paper should have a look at it, have a shot. It is a highly mathematical thing. It is concerned with formula. There is no hint that it might be the basis of any practical design. I would not have said that had any what it is.
Now, interesting conjecture is this, though. Turing was working at the Institute for Advanced Studies where von Neumann was. When von Neumann first visited the ENIAC, he immediately made the suggestion that they should, in fact, make use of the function boxes of ENIAC to store instructions. In other words, the concept of the
That was much later.
Yeah, yes,
the ENIAC had been running for
sure, yes,
several years when that was done.
yes, right. Yeah.
That wasn't very obvious.
No, but this seems to me indicates that Turing must have had a good bit of contact with von Neumann in those early days. In fact, von Neumann must have been familiar with Turing's work. So it could be that the introduction of the idea of a stored program computer came via that route, though it's only conjecture.
Well, I knew Turing very well, and I used to speak to him quite a lot when I went to Manchester. And we talked about these things like that. And Turing at that time told me that he'd been besieged on it from Neumann, and they discussed computer things at that time. And the suggestion was that some idea, Jonathan Neumann, hadn't been thinking, that was many, many years ago, hadn't been thinking about it beforehand. Now afterwards, I think Turing's, and what he said to me, that Turing's design and his general idea of how a computer ought to be, that was his own scheme. I don't think that came from America. That's my own view, talking to him quite a lot.
Can I make my point clearer? I think the concept of a stored program computer is extremely clear in Turing's paper, with which I'm extremely familiar. In fact, just to give an anecdote, I found a large number of errors in the actual programming of his universal computing machine, which I went along to talk to him about, and found he was very intolerant of anyone finding errors. In fact, it was a common thing for Turing to make programming errors. He wasn't a awfully good programmer. And in fact, subsequent designers of universal computing machines, like Minsky, also made errors in their program, but they were a bit more gracious about it when I pointed them out. Anyway, the concept, I think, is there very clear. And what is more interesting is that the concept of interpreting the instructions of one machine to make another machine was also extremely clear in that program. What I'm not claiming, and I agree with Morris here, is that this had direct influence on the post-war development of computers, except conceivably by the indirect route that it must have been well known to von Neumann, who I think probably had first really sort of thought about stored program computers at the time when he made this suggestion to the ENIAC team. That's only an objection. But the concept was there, even though it may not have had a direct influence on the work of it.
We don't know that von Neumann made that suggestion. People were counting from model.
Oh, see, the anecdote I heard was that when von Neumann was first shown the ENIAC, he immediately pointed out that the function tables that they set up could be treated as instructions to save all the replugging.
But there's no evidence.
I see.
No evidence, no, I mean, you may have heard.
Can I put a different question? I'd always got the impression, may have been wrong, that the idea of a program was quite old, but the really essential thing was that the program could operate on itself. Now, were there not relay machines like that made by Zuse, for instance, which had a program? The program and the numbers that it worked on were quite distinct.
Yeah.
The real essential, powerful idea was to make the program operate on
That
itself.
first appears in 1936 in Kilurn's paper, no doubt. I think the paper was a mathematical paper and not intended to be a design of a practical machine.
Okay, let's come off of that point. And we come back to the more clear subject of the seminar, which is the design decisions on the early computers. Does anybody have any other comments or questions to the speakers in more general terms? Yes, Doran.
It's not directly related to the design decisions. What I'm curious about is the physical fate of any of these machines, particularly say Mark I, whether anyone is aware of the circumstances in which they were disposed, and whether there's any awareness at the time that these were, at that stage, historical items.
I can say something about that Mark I. It was in the Science Museum and refused. Then put in a room at Ferrantes, in what Ferrantes hoped to develop into a museum, and it stood there occupying valuable space so long that it was finally scrapped, which is a pity.
Yes.
Well, I could say what happened to the DR1. It was so enormous, I said it had to be got rid of. There was about half a ton of mercury in the store, which is the only valuable thing that came out of it. It was sold for 3 times what it was paid for. The price of mercury had gone up 3 times. We have delivered certain small pieces to the Science Museum, where they still are. It was far too big to do anything else with it, so the rest of it was just junk and scrap metal.
Unfortunately, the Ace pilot model was reasonably small and is actually in the same.
Yes.
I picture, it seems to me, that was true over Tom Kilburn's circuitry and stuff we did at NPL. It was very, very much designed in such a way that it didn't matter how the bells worked too much. So they could deteriorate very badly and still work because of the special sort of techniques they were used. And I often wondered to what degree both of them, because they were different sorts, to what degree both came from Blumlein, because Blumlein spent a lot of time in his early days at GRE. And I wondered if Tom Kilburn would know anything about that.
Yes, I think I became a circuit engineer. I was a mathematician reading undergraduate mathematics at Cambridge when I was called up and sent to GRE into F.C. Williams Group. And it was F.C. Williams who converted me, or almost converted me, into becoming an engineer. And he was a great admirer of Blumlein. Blumlein was killed, wasn't he, in an accident?
That's right. Well,
and I always say, when I'm talking to people, that probably Freddie Williams was the best circuit designer after Blumlein. But I know that that Freddie Williams was a great admirer, and there's a direct connection there, is what I'm saying.
but I do know that Blumlein was a lot older, of course, than Freddie.
Yes.
And Blumlein went in and had him working for him early on. So it seems that Freddie probably got a lot from it. And what you say. So I think you will give full marks to Blumlein.
Does,
Indeed, yes.
does that imply that the effect the effect from the EMI team of which Blumlein was a part is that a strong source of electronic circuit design used in
Yes.
Yes, absolutely.
Very definitely.
It's very interesting, actually. There was another circuit called an anode follower, which all of you will know. And we used the anode follower to design as the cheapest method of designing a digital ladder for subtractor. And in order to do this, we were using the anode follower to actually sum in an analog way the input pulses. So the basis of our digital ladder was in fact an analog circuit called the anode follower, which I think arose from Blumlein too.
Those who may not be familiar with cathode coupled or long-term pairs, of course, emitter coupled logic is precisely the same as the transmitter.
That's right.
Yeah, I mean, just in case the connection hasn't been.
I would like to make a remark about Blumlein's work, having had a very good look at the design of the H2S radars in his laboratory. One of the stories I heard about him, probably Ted can confirm this, was that he would not allow the circuit to be used if you couldn't tolerance it. And at the time, the tolerancing of circuits was a very little practiced art. And he insisted on circuits being properly toleranced, and as a result, the H2S radar was fully toleranced, and in some cases there had to be 1% resistance in it. But at least you'd be sure that if you put the thing together with the correct combination of tolerance components, it would work. You didn't have to fiddle with it to make it do so. There were no adjust-on test components in his circuits. And I think he set the whole scene for circuit design, raised the whole level of quality of design of circuits very considerably by his own efforts. I'm quite pleased with that.
Well, I can confirm that because I was a nice boy. But I mean, when he was doing all this stuff, I was having to say then why things were going on. And in fact, after Blumlein died, I took over about half of the H2S staff at the EMI. And so what's been said about this very careful function and making circuits that you could tolerance. That's the
right.
important thing.
Choosing circuits which was open to analysis and only those sorts of circuits. And in fact, the circuit we showed was a very, very good example where the current was well defined, where fairly large voltage drop across resistance. It didn't matter too much about what the mutual conductance of the valves was.
One thing that Clayden didn't point out is that on those circuits there are voltages between plus 300 and minus 300 volts. You had to work on those while they were actually working. That's good for you. What he mentions in his paper is that you've always kept one hand away from the circuit.
One hand in the pocket.
One hand in the pocket.
Unearthed soldering irons.
I never never switch off when I'm repairing range things nowadays. It's trivial compared with
Yes, Jeff.
We've heard an awful lot about the hardware side this afternoon. I mean, one thing that I think is very well known these days is that hardware engineering and software engineering are very different. And software never seems to get to the same level of control and organisation. Now, a lot of what we've heard this afternoon has shown in these last points about how good engineering principles were at the back of every single project, whatever they were doing. And this led to successful machines using very difficult circumstances, difficult and so on. When people were doing their programming, were they applying the same care and sophistication to the way they programmed? If they were, why didn't software develop properly in the same way? And if they weren't, why did they have a different distance?
I'd really like to challenge the basic assumption there. What happens is that when machines get beyond a certain size, software doesn't catch up with it. But in the very early machines, I would guess, is the only one that I know was Nexus, and that I think the software was extremely sophisticated. The software run marvels out of the hardware. And to some extent, if you look at some of the early personal computers where the constraints are very tight and very similar, you see some of the same things happening again. And then when the machine gets beyond a certain size, the combinatorial explosion takes over a number of things you can do, and it's impossible for the software to keep up. But it's really the other way around. On a very tightly constrained piece of hardware, then you see much more nearly optimized software.
But the actual hardware introduced a new discipline of software, didn't it? So there was no background software as such before these machines existed. So the software had to evolve, whereas the hardware already existed. Well, it was configured in a different way, surely.
Well, that as well, but on a very small machine, you fill up the software possibilities quite quickly. And even if you have a great tradition of software on a very large machine, you never will.
David, you wanted to make a point, I think. David Wheeler.
Oh, well, I wasn't quite sure about this. I mean, in the early days, hardware, people talk about individuals actually making a computer. A large number of circuits working together, and many interaction problems which had to be solved using the hardware. They turned up and they were solved. In the same place, the same things took place with software. As programs grew, were more interactions possible and they were solved. I don't think there's any real difference between the two. I should point out also that on the hardware, you only see the survivors who are fair enough projects of that era, which are not represented here today for various reasons.
How about the assertion that hardware scales up better than software?
I think it's a bit...
I would deny that. I mean, the hardware scaling up nowadays relies on software, so the software has to work as well as the hardware.
I think the software is, the early software was much more sophisticated than people think. Because, of course, what we had to do in those days, all our code were numbers. I mean, there was no helping about that. But we started getting quite sophisticated about subroutines. And we did very hierarchical sorts of ways of doing things. So, for instance, when these columns were getting together to do different things, you'd have a little subroutine, then you'd have a higher level subroutine and a higher level subroutine. And some of these systems that we worked out for doing matrix works and things like that were really very sophisticated and worked extremely well in a hierarchical sort of way. But I think when the high-level languages came into being, they came into being rather in a way to try and make things easier for people and not to make them more sophisticated in engineering.
Yes, I speak with some experience
have your name, please?
Roger Scantlebury.
Yes.
I was part of the time working on the ACE computer, and I remember servicing the machine with Jim Wilkinson standing over me. And one of the tests, we'd run a series of tests on the machine, software programs written to test the machine. But it was a pretty poor machine past its own test programs. So as a final test, we would run one of Jim Wilkinson's big matrix programs. And if it ran that, you got it right, then it was a good machine. And if it didn't, it wasn't a good machine. That was the acid test. The hardware was actually being tested by a sophisticated software which was known to work. But there was a small rider to that, which one day the team wouldn't pass this particular program. And therefore Jim swore there was something wrong with the machine. He swore there was a bug in it. And we couldn't find this bug. And eventually, we actually reproduced his pack of cards and ran it on the new pack of cards, and still didn't pass the program. So I wound up by taking every single card, one by one, and comparing the lace pattern that Donald's spoken about on the tolerant cards. Until I found one card that got one bit different. And when I found that card, I looked at the bit, and it was a Chad that Wilkinson put back into the hole. Then pushed into the hole with a pencil. And the pencil lead was conducting through on the
Well, it is now. Yes.
Yes. Brief mention has been made of marginal testing of machines. And I feel that's a very important point that present-day equipment's lost sight of. On the ACE, for instance, we would have a test program, like the one Roger just mentioned, run to give confidence in use. And you have one master switch on the control desk that can change all the biases up and down at every stage of the machine. If that failed, you could then subdivide it. You can do the same test on each frame. And if you found the frame where the fault was, you could subdivide again and do it on each chassis. Very powerful means of fault diagnosis and confidence boosting. And present day technology seems to have lost sight of that.
Just to come back on that one, I think the technology, today's technology is slightly different. It doesn't work in the same way. When marginal testing was, I believe, implemented to catch the bound, has gone beyond the limits. This is my experience of complexity. But you don't get fortunately, you don't get the same type of deterioration in semiconductor device. You don't now, anyway.
Right, well, I think we should draw it, it is 5:30, I think we should draw it to a close. I found it to be absolutely fascinating, I'm sure you all have as well. And what I would like you to do is to finally thank all the speakers for their efforts in this thing this afternoon. Just say that the next meeting of the Computer Conservation Society is an evening meeting on June 28th, when we are having a discussion on software and how we should record the history of software and historical software. And then on the 11th of October, we have our open day, when the machines which we're restoring, I am told, will be working. And finally, a very final point, I think I'd say those of you who would like to come for a brief dinner at 6:30 are welcome to join myself and some of the speakers for that down that way.
Could we ask the speakers to join us for a photograph? Together for a photograph.
Yeah.